Picture an LLM server handling a wave of user requests all at once. To use the GPU efficiently, it groups them into a batch and runs them together. But here's the snag. Every user's answer is a different length, so they finish at wildly different times. With the naive approach, the whole batch has to wait for the slowest one before anything new can begin, and while it waits, most of the GPU just sits idle. Wouldn't it be far better to swap finished requests out and fresh ones in continuously without ever stopping? That's exactly what continuous batching does, and it's one of the biggest wins in modern model serving. Let's dig in. At its heart, this is a scheduling idea that operates at the level of a single token step. Follow how a request moves through the running batch, one stage at a time. Start with a batch of requests generating together, token by token. Each user prompt is producing its answer one step at a time, all sharing the same forward pass, so the GPU processes them efficiently in parallel. So far, this looks like perfectly ordinary batching. Now a request finishes. Its sequence hits a stopping point while the others are still going strong. Instead of making everyone wait for it, or making the newcomers wait for everyone, the scheduler evicts that finished request from the batch the very instant it completes, freeing its slot. Then a waiting request slots straight into that freed space. There's almost always a queue of pending prompts, and the scheduler admits one immediately, so the vacated capacity gets reused on the very next step rather than sitting empty and wasted. Finally, the batch stays full, because requests are evicted and admitted continuously. Every step at every moment, the GPU never drains down and idles waiting on stragglers. That constant refilling is the whole trick, and it keeps the expensive hardware saturated with useful work. So how much does this really change things? Here's the old way against the new, side by side. Static batching groups requests, runs them together, and refuses to start anything new until the entire batch is done. So if a single request generates a long answer, every request that already finished just sits there, holding its slot, while the GPU burns cycles on a nearly empty batch. Utilization quietly collapses. This technique, also called in-flight batching, works at the granularity of a single token step. The moment any request finishes, it's evicted and a waiting one takes its place. So the batch is refilled continuously and the GPU stays busy. Systems like VLLM and TGI use this to serve many times the throughput of the static approach. Strip it down, and three ideas make continuous batching powerful. It refills the batch every token step. Rather than treating a batch as a fixed group that starts and ends together, the scheduler continuously evicts finished requests and admits waiting ones, so the batch composition changes on the fly at every single step. It keeps the GPU saturated. Because there are no long stalls waiting on the slowest request, utilization stays high and throughput climbs, often to many times that of static batching, which directly lowers the cost per request served. It pairs with paged key value cache memory. Slotting requests in and out means flexibly allocating each one's growing cache, which is why continuous batching works hand in hand with techniques like paged attention inside serving systems, such as VLLM and TGI. All right, let's lock in what matters. This serving technique keeps a GPU busy by swapping requests in and out a running batch every single token step. It fixes the flaw of static batching, where finished requests sit idle waiting on the slowest one and the GPU waste cycles. By evicting completed requests and admitting waiting ones instantly, it keeps the batch full and delivers many times the throughput. It pairs naturally with paged key value cache memory, and it powers serving systems like VLLM and TGI. If you enjoy seeing how models actually get served at scale, there's plenty more waiting for you at standarity.com. See you inside.